In this last video for section 2.4, we're going to take a look at a particular surface area example. This one's a little bit tricky, and it's not obvious why it's tricky kind of from the get-go. So let's dive in. We've got the base of a lamp is constructed by revolving the quarter circle y equals square root of 2x minus x squared on the interval from 1 to 2 about the y-axis, and we want to compute the surface area of the lamp base. So again, it's going to be helpful to have a picture. So let's think about at least this region that we've got set up here. We have this function y equals root 2x minus x squared, which isn't what we're used to seeing as far as circles go. But it's not too hard to show that this is, in fact, part of a circle. So if we square both sides, we can start with y squared equals 2x minus x squared. And moving everything to the same side of the equation, we get x squared minus 2x plus y squared equals 0. And what I want to do here is complete the square in order to get this looking like x plus or minus something squared plus y squared equals something. So in order to do that, I recognize that these first two terms here, this x squared minus 2x, well, that's a square if there's a plus 1 there. So I'm going to add 1 to the left-hand side and 1 to the right-hand side. And then I can factor this as x minus 1 squared plus y squared equals 1. And now I know that this is a circle with radius 1 and center at the point 1, 0. So if I kind of find that point here, then the circle that I've drawn is this circle here, because I'm looking at the top half of the circle because I've taken y to be the positive square root here. So I have my half circle here, but I'm also focused only on the interval from 1 to 2, kind of what the problem statement gives me. So that's where this kind of quarter circle is coming from, because I'm just focused on this part of the circle. Then what I'm doing is I'm taking this part of the circle and I'm revolving it about the y-axis, sort of giving me some kind of shape here. Let's see if we can draw it. So there's kind of the top. It's going to have kind of a circular side there and a circular side here. And then we're going to get something like this. And then it's going to go around. And we have a surface. Great. So this is kind of perhaps plausibly the shape that you might make if you wanted to make a base of a lamp. And so what we want to do is take the surface area of this shape. So there's sort of a question of, do we want to integrate with respect to x or with respect to y? And it's not obvious. One of them is going to work, one of them isn't. So let's start with the one that seems a little bit easier, which is going to be integrating with respect to x. I certainly have y as a function of x right now, so that maybe seems like a slightly easier thing to do here. And as with the previous problem, so we want to integrate from the left end to the right end the surface area of one of these shells that we get. So we know that the surface area is going to be 2 pi times the radius of the circle that's formed. The radius of the circle that's formed will be the x-coordinate of the point in question. And then we're going to take the area, or the length differential that we're multiplying it by in order to get the surface area of this thin strip. Since we're integrating with respect to x, we want to have that surface area differential be dy over dx squared dx. Great. So working through this, we're going to get the integral from 1 to 2 pi x times the square root. Let's see, if we have y equals root 2x minus x squared, let's see, and we want to find dy dx. Where should we put this? I suppose maybe we can put it underneath our original integral here. So y equals root 2x minus x squared, so that's going to tell me that dy by dx is equal to, using my chain rule here, so this is going to be 1 over 2 root 2x minus x squared, times the derivative of 2x minus x squared, which is 2 minus 2x. And we can cancel out some 2's, giving me a 1 minus x over root 2x minus x squared. So what I want to do now is look at 1 plus this derivative squared, so 1 minus x over root 2 minus 2x, over root 2x minus x squared dx. And I'm going to tell you right now, before we go through any of the arithmetic, that this is the way that's not going to work. This maybe looks like we could manipulate this inside expression here and do something good with it, and it turns out that it doesn't turn out badly. It just turns out to not be particularly helpful when we look at this integral as a whole. There's not really a good u substitution that we can do. There's not really much further arithmetic that we can mess around with, and so we kind of end up stuck. So after we do this, we actually need to go back and we need to think about integrating with respect to y. And so again, what we want to do is we want to set up this integral. We want to think about the now lower bound and upper bound on this region. So the lower bound is going to be this y equals 0, and the upper bound is going to occur here at y equals 1, since we found that this circle had radius 1. So we want to integrate from 0 to 1 this time. Again, we're going to want to take 2 pi times the x-coordinate of a given point, because that's going to represent the circumference of one of these disks. So if I take 2 pi times an x-coordinate, well, I had better solve for x in terms of y here. So I'm going to use this formula that I have here, because that's going to make it easiest to solve for x in terms of y. That x minus 1 squared plus y squared equals 1. So we're going to come back to this integral here in a second. For the moment, we need to think about this formula, x minus y squared plus y squared equals 1. We want to solve for x in terms of y. So this is going to be x minus 1 squared equals 1 minus y squared. We want to take square roots on both sides. And so that's going to give me x minus 1 equals, and we want to think about whether we want the positive or negative square root here. We'll maybe decide on that later. We'll be taking one of the square roots of 1 minus y squared. And this is going to tell me that x equals 1 plus or minus the square root of 1 minus y squared. In order to decide whether we want the positive or negative square root, we are going to look at whether or not x is bigger than 1 or less than 1. If my x values on this curve are bigger than 1, then I want the positive square root here, because that will give me x values that are bigger than 1. The negative square root is going to correspond to x values that are less than 1. And if I go back to the circle that I have, I see that the x values on this curve are bigger than 1, so I want the positive square root. Great. So now I can go ahead and fill out this information here. So 2 pi times the x-coordinate of 1 plus root 1 minus y squared times the square root now of, we want to be integrating with respect to y here, so what we're interested in is 1 plus dx dy squared dy. Great, so we need to take dx dy. Dx dy works out to be, let's see, so we again, the derivative of 1 is 0, so that goes away. We have divided by, we have 2 root 1 minus y squared here, times the derivative of 1 minus y squared is a minus 2y. And so we end up with minus y over root 1 minus y squared. All right, so let's see. So actually working towards an integral here, it certainly seems like this is going to be worse than the other case, but it's going to turn out not to be. Square root of 1 plus dx dy squared here. So we just found that dx dy was minus y over root 1 minus y squared. We're squaring and integrating with respect to y. All right, to further simplify, 1 plus root 1 minus y squared, square root of, well, let's put the square root in later. We have 1 plus, so we have a y squared in the numerator there, and a 1 minus y squared in the denominator. Combining this 1 in, we know this 1 we can represent as 1 minus y squared over 1 minus y squared. And then in order to add these fractions, now that we have a common denominator, we can add the numerators. And we notice that the minus y squared in this numerator and the plus y squared cancel out. Great. 0 to 1, 2 pi. 1 plus root 1 minus y squared. Let's see, we have a square root of 1 over 1 minus y squared. And we can think about this square root here as being the square root of 1 over the square root of 1 minus y squared. Well, great. The square root of 1 is just 1. And now what we can do is we can distribute this term into these parentheses here. So if I am integrating from 0 to 1 here, 2 pi times 1 over root 1 minus y squared. So I've multiplied 1 over root 1 minus y squared by 1. And I've added that to root 1 minus y squared over root 1 minus y squared. And we're getting close. Integral from 0 to 1 of 2 pi 1 over root 1 minus y squared plus the root 1 minus y squareds here cancel out, so that's just plus 1. But now, lo and behold, we have simplified this to something that we can integrate. I know the integral of 1, that's y, and I know the integral of 1 over root 1 minus y squared, that's arcsine. So this is equal to 2 pi times arcsine of y plus y, evaluated from 0 to 1. So all this work, and we get a relatively straightforward looking function here, but what we can do now is actually compute. So arcsine of 1, I know, is pi over 2, because that's the angle that gives me a y-coordinate of 1 on the unit circle. If I evaluate at 1, that becomes plus 1. And let's see, so now we want to evaluate at 0, and if we evaluate at 0, arcsine of 0 is 0, y at 0 is 0, so that gives me nothing as a matter of fact. And we end up with this quantity here. So all of this work is going to give us a nice answer for the surface area, despite, taking a while for us to get there and us having to go back and sort of try again with integrating with respect to the other variable. So you can see here that these questions are really tricky. It's not obvious what the best starting place is. Sometimes if you start somewhere, you're going to have to abandon that starting place and go back and retry. So I guess maybe what I want to do is sort of emphasize that getting something wrong to start is okay. And sometimes if you don't know where the place to start is, sometimes it's best to just start somewhere, see if that works, and if it doesn't, go back and try the other option that you had. There's certainly no shame in getting the starting place for this problem or any problem wrong. So keep that in mind. This section is hard. It's going to be a bit of a struggle. It's going to take a lot of work to do a single problem, and that's okay. We're going to have, the homework assignments from this section will not include lots of problems. They will include few problems, but it should take you a while to work through each of those problems individually. And that's okay. That's just kind of the nature of some of this integration stuff.